Very good morning, everyone. Welcome to the third session of Industry Forum. I'm Rupa Kamuji, Director R&D from Synopsys. I will be hosting this session this morning. So we have lined up presentations from various industry leaders. So the first two talks are based on the topic SoC design optimization. Speakers from Qualcomm will deliver the presentation in two parts. First part will be delivered by Rishabh Khurana, who is a technologist with expertise spanning VLSI, system design, and machine learning. So he has 15 years of industrial experience and has delivered innovative R&D products in analog and mixed signal and machine learning. So he will be taking us through SoC design optimization using machine learning. So Rishabh, over to you.
This is part 1 of the talk on SoC design optimization using machine learning. Through this talk, I'll mention the current challenges that we face in SoC design optimization and how machine learning can help circumvent some of those challenges. Over the years, SoC designs have become extremely advanced, with more and more IPs getting integrated into single SoC. This progress has been enabled by few key industry pillars: ability to design fabless chips, ever-improving and sophisticated design automation tools, and better computing hardware for running EDL algorithms. The supporting technological trends for these pillars were PPA scaling with TechNode, sophisticated optimization algorithm development, and compute infrastructure for high-speed and parallel processing. But lately, these industry pillars are under threat and are at risk for disruption. Few reasons are: fewer PPA gain from TechNode scaling almost 50% less, leaving designers to explore more to achieve same amount of PPA gains. Exponential rise in corners to be supported, making current optimization algorithms slow, thereby increasing design time, and increasing cost of compute infrastructure needed to run sophisticated and slow algorithms. We will now look at one of those key challenges, diminishing PPA gains with TechNode scaling. If we plot PPA gains from TechNode scaling over recent TechNodes, we see a declining trend in percentage PPA improvement. The chart shown depicts conceptual trend with percentage PPA gain on y-axis and TechNode on x-axis. It highlights how historical gains available from TechNode scaling have slowed and are projected to further slow down in future TechNodes. With declining PPA gains from TechNode scaling, every SoC design is getting more challenging. Designers now have to optimize every IP to squeeze out max PPA gain. To sustain PPA scaling, required design advantage is on the rise. This has mandated wider design space exploration. But this has to happen with constant operating cost and within similar design timelines as before. To manage the design complexity, designers now require newer design tools. If we take a holistic view, required design tools need to ensure that designers are able to meet key business metrics while optimizing design. The design process has to ensure that chip area doesn't increase while maintaining good yield. The process also has to keep test time in check and support newer chip packaging technologies. The process should also lead to better design efficiency by reducing number of design iterations at every stage. It also has to make sure that the power and performance trade-offs are well captured at every design hierarchy. And this process should have minimal impact on required computing cost. In essence, design process with new tools should enable maximum PPA optimization, wider design space exploration, and meet all key business KPIs. How does our current design process look like? Our current design process, be it front-end design, physical design, or design verification, starts with designers selecting the design variables, whether it's placement of memories, or test vectors for DV, or recipe for synthesis, and is followed by running accurate EDA tools for design evaluation, and then assessing the quality of result metrics. Based on the QR results, designer then decides on next design parameter optimization, completing the loop. This loop works and works well, but takes many iterations to converge, and with every iteration having longer turnaround time. With deeper design exploration now required, this loop has become a bottleneck. To remove this bottleneck, we need to address two key points: how to reduce the number of iterations, how to reduce the time spent per iteration. A solution could be to automate this loop, but automation scales exponentially with the complexity of design. So another solution could be to reduce the time to evaluate a design. Currently, evaluation of every design still takes days or weeks. We can approximate the QR metric with the help of faster tools, but then this approximation leads to suboptimal designs. One of the byproduct of multiple iterations is that a lot of data gets accumulated, which brings the question: can we develop data-driven design tools to reduce design time? One of the key machine learning technologies that we have heard about in the news is reinforcement learning, which has achieved superhuman performance in games like chess, Go, and other games. Reinforcement learning is a data-driven sequential decision-making framework. So a natural question is whether we can leverage the same reinforcement learning technology to reduce number of iterations. We have seen a few good research papers on using RL for design optimization, but those papers are essentially written by people from AI research community, and they fail to address the key factors of semiconductor engineering. SoC design is a constraint optimization procedure, but reward design in RL is not designed for constraint optimization. Reward maximization doesn't guarantee all design constraints, and it pays no regards to downstream design stages. Additionally, to get accurate reward, we need to run EDA tools, which can take hours, days, or weeks. So unlike in other disciplines, where reward is easily accessible, it's not available in SoC design. To shorten the time to reward, typical approach is to approximate the reward, but then approximation leads to suboptimal design. SoC design is also a creative process, and it's difficult to list down all the actions that designers take, further rendering RL difficult to apply in SoC design optimization. Another key machine learning type is supervised learning, which we have seen to work across multiple disciplines like computer vision, language translation, and recommendation systems. We believe this machine learning technology is a key to solving SoC design challenges. Using supervised learning, we can develop tools that learn QR metrics as a function of design parameters. This problem formulation correlates well with what designers require to optimize design. They require a tool that can provide them with correlation between QR metrics and design choices, and subsequently helping them quickly converge on design parameters. This tool can provide quicker feedback to designers, reducing the time spent per iteration. But what is supervised learning? Supervised learning starts with collecting data, which in case of SoC design would be past design iterations data and their respective QR metrics. Then a machine learning model that learns the mapping between design characteristics and QR metrics is trained. The training is usually done by minimizing a loss function that measures some notion of difference between actual target and predicted value. Although applicable to SoC design optimization, research is required in several key aspects of supervised learning for it to be made feasible for SoC design optimization. Few research areas are data representation. Unlike images and languages, our design data exists in the form of netlist and placements. For us to train any model and that model to learn, we need to make sure we represent our netlist features well. Another research area is engineering of loss functions. A lot of innovation is required in supervised learning for loss functions that can capture difference between achievable PPA KPI and predicted PPA KPI. Research is also required in what models to train. Convolution neural networks, recurrent neural networks, transformer models aren't directly applicable. Unlike other ML application domains, data is limited in SoC design, and research is needed in training from limited data. Pre-trained models are available either, and also not applicable since data domain is very different from other AI domains. Finally, we need a stronger validation strategy for our models that generalize across heterogeneous SoC designs. We need a framework to continually monitor progress, shorten the model tuning loop, as our SoC design space is non-stationary. So we believe the threats to our key pillars of advancement could be mitigated with the help of AI, which can enable data-driven learning, can capture nonlinear and non-stationary dynamics, and will lead to wider and continuous design optimization. In the second part of this talk, my colleague Lindsay will dive deeper into the machine learning challenges and respective research required for SoC design application. Thanks everyone for attending and listening to the talk.
Thank you, Rishabh. Thank you for the wonderful talk. So it really opens our eyes in about the challenges that are there in the SoC design. So you already mentioned about challenges, especially when we talk about machine learning, right? So the major hurdle is getting the data. So as you said, there is a lot of research being done in that area. So I mean, can you give any sort of like glimpse on how, because it's about representing the netlist, right, as a test data. So what kind of research you see happening in that area? You're on mute, Rishabh. Can you unmute? Yeah.
Right. Yeah, my video had got stuck earlier. Sorry. Yeah, that's actually a very good question. And Lindsay, my colleague, like I mentioned in the second part of this talk, will go deeper into that.
Mm-hmm.
But the few pointers that we have seen so far, netlist consists of connectivity, right? And we have to learn from all the connected substructures. In addition to all the features or the aspects of nodes in the netlist, right, or the cells in the netlist. We have seen over the years that graph neural network are or graph representation of the network or the netlist, followed by the graph neural network modeling architecture, seems to generalize well and work well within netlist area space. But like I
Okay.
said, in addition to that, we do need more innovation because connectivity is one part of it, and it's a multimodal system, which Lindsay again will go deeper into. It's not just about connectivity, it's also about placement, it's also about logical structure, and so on. We have to learn from all those aspects to be able to generalize and to make a stronger claims.
Yeah, yeah, yeah.
So pretty much that, and also as I mentioned, that the data is extremely limited in SoC design. We get few snapshots of maybe 5 to 10 chips per year. I don't know, maybe even lesser than that in some places. To maximize based on that, we do need to be able to design features of the netlist that are also that do provide some domain expertise. So we always need to keep domain experts in the loop.
Correct.
It's not a pure machine learning task as such, unlike in image and natural language processing.
Okay. Yeah, I understand the challenges there, and yeah, I wish good luck to you and Lindsay, the two researchers working in this. So, thank you so much for the wonderful talk. Thank you.
Thank you, Rupa. Thanks for the opportunity.
Thank you. Okay, so now let's move on to the second part of the presentation. So the second part of this presentation will be given by Lindsay, who is a staff machine learning engineer at Qualcomm. She has led multiple projects in ML-based CAD or EDA, which have impacted global SoC design process, leading to significant savings in time to market, compute, or NRE cost. So she holds 3 pending patents related to this work. Apart from her professional life, she is passionate about cooking and sports, in particular tennis, boxing, biking, etc. So Lindsay, stage is yours.
Hi, my name is Lindsay Costas with Qualcomm Machine Learning Research, and I'll be giving the second part of this 2-part talk on SoC design optimization using machine learning. The first part of this talk motivated why predicting PPA is so important for the future of SoC design. We need to produce the most competitive chip at the lowest cost and with the least amount of effort. Effectively, we have a multidimensional optimization over power, performance, area, and effort. This optimization problem is challenging, in fact intractable when applied to the full SoC design, due to the fact that the SoC is composed of millions of objects. This challenge is met today with a divide and conquer approach, where the full design is split up into a set of hierarchies, and each of these hierarchies is optimized independently over a set of different modalities. Starting with a schematic view, then moving to a netlist view to capture the connectivity, finally being realized in the physical design, where each hierarchy is optimized independently, then stitched back together into a final SoC. As such, predicting PPA is not sufficient. Rather, we need to predict PPA across the hierarchies and across the modalities. The first part of this talk also motivated why machine learning can be an effective solution to this PPA prediction challenge. In particular, machine learning is a very effective framework when dealing with large or complex data where a person or an analytical approach will struggle in the face of such complexity. In this case, the data is, however, the defining challenge of the machine learning solution. The data is limited due to the high cost in compute and runtime to produce large sets of quality data on which to train models. This is due to the cost entailed of running synthesis and PNR on many designs. The data itself exhibits dynamic relations. We have a fully connected SoC design, which we have split into different hierarchies and modalities. As a result, when we make a change in any one of these hierarchies or modalities, that change will impact at least part, if not the full rest of the SoC design. This introduces the third challenge of partial observability. When such a change is made, and that cascade effect does happen, we don't have full visibility due to the fact that at any given time, we're usually focused on just a single view of the data. Finally, the fact that we are operating on different hierarchies and modalities, and these hierarchies and modalities are quite diverse, we need a solution that, given a subset of these views, can be applied, learned, and then generalized to the rest of the design. And this solution is important because we are dealing with limited data. So in sum, we need innovations in both the data representation and the model architecture to truly provide a machine learning solution for the PPA prediction problem. To understand why we need innovation and can't rely just on the state-of-the-art as it exists today, we need to look at the past. Algorithms are incredibly powerful rule-based decision makers. However, they struggle in the face of learning dynamic relationships. And that's exactly what we need to do. We need to be able to learn patterns from our data in order to generalize. For example, if we build an algorithm which can work for, say, a modem, that algorithm will be great for the modem and anything that looks like a modem, but it will fail when applied to something fundamentally different, for example, a CPU. To address this, we truly need something that can learn from patterns. And this is where machine learning comes in as an effective framework. However, the classical forms of machine learning are not sufficient to handle the complexity of our data, specifically the multimodal input and those dynamic and partially observable relationships. For this, we need something much more complex. And thankfully, that's where deep learning becomes so effective. And in fact, we have seen state-of-the-art solutions being applied from various deep learning domains to SoC design problems. For example, researchers have discovered that they can think of data paths as sequences, much like people think of sentences as sequences, and as such, they're applying state-of-the-art language solutions to SoC data path problems. Similarly, people are looking at the physical layout of a chip and its multiple metal layers, like an image which has multiple RGB channels, and as such, they're mapping state-of-the-art vision solutions to chip design problems. Now, while these applications have been tremendously powerful in providing a first set of machine learning-based SoC problem solutions, and also giving us much greater understanding and insight into how ML can be effectively leveraged in the SoC design domain, what we do see is that each of these solutions is not sufficient in its ability to capture the multimodality aspects of the data or those dynamic relations, and as a result, they don't meet the performance spec that we need in order to turn that research into a deployable solution that could be used in a real tape-out. The result is that 50 plus years of ML R&D to build these state-of-the-art solutions are still insufficient to solve our PPA prediction problem. And this motivates the rest of the talk. We will focus on a newer class of deep learning solutions, specifically graph neural networks. And the rest of this talk will really motivate why graph neural network-based innovations will be the thing that will drive machine learning solutions for SoC design. Now, to understand why graphs and a graph neural network are so powerful and important to this problem space, we need only look at what an SoC is. An SoC is composed of circuits. And circuits, whether they're digital or analog, are natural graphs. In the case of a digital circuit, we can think of the gates as nodes in the graph and the nets that connect those gates as the edges. And then each of these nodes and edges can be annotated with features to describe them. An adjacency matrix can be constructed to describe the connectivity of this whole system. And then with this, what we have is a single representation that captures not only the hierarchy, but also the schematic, connectivity, and placement modalities of our data. And why this is powerful is that once we have this in a single representation, we can use that graph neural network structure to model the dynamic relations that classical representations of vectors and matrices fail to model. So we see that a graph provides that foundational input representation we're looking for, and a GNN is that innovative model architecture that can support this representation. Much like any state-of-the-art machine learning solution, we too still require lots of data on which to learn. One solution is to produce large sets of real data. However, this comes at a cost of huge compute, and as a result, violates our effort constraint. An alternative would be to generate lots of synthetic data. Now, while this addresses our concern about effort cost, the data itself is approximate, and so we can't learn to the accuracy or the quality that we need to, and thus we violate our power and performance constraint. So what we see is, although we have the right input representation and a model architecture that can model that, we're still lacking in terms of our ability to translate that into a productizable or deployment solution that truly solves the PPA prediction problem. As such, this really motivates why those vanilla formulations of the input representation in the model architecture are a great foundation, but much innovation is needed on top of that to truly solve our problem. And why innovation is needed on top of what exists today? To understand this, we only need to look at the landscape of machine learning research and development over the past 10 years. There's no doubt that the amount of research and the gains that have been made is tremendous. If we look at the number of papers that are published, over about 100 more papers per day are published now than were published in 2009. However, when we take a close look at what is contained in those papers, we see that the research and the advancements fall into three broad classes. The first class is fundamental research and development. Now, this class of work, it makes tremendous strides forward on the research side of machine learning. And this is where you're producing breakthrough new model architectures. For example, this is where all the new GNN networks would sit. However, what we see with these class of work is they are aimed at fundamental R&D. So they're not aimed at whether the solution they're building could be deployed in a specific application. And as such, these solutions don't meet our PAE criteria. They're violating at least one, if not more, of our power, performance, area, and effort constraints. A second class of research papers are oriented at taking these fundamental R&D gains and extracting out that nth bit of performance. So rather than focusing on how do I make this great new architecture deployable, they're focusing on how do I make this great new architecture even more accurate. And while this is great in terms of increasing our understanding from a technical core machine learning perspective, what it doesn't address is it doesn't address how do we actually make models useful for practitioners. And much of the focus of this work is really geared at tuning parameters, adding an extra layer, replacing a different activation function. The final class of work where we see a lot of research is it's on the applied side, and we see people recognizing and taking existing deployable solutions, seeing their value, mapping them to a very similar problem space but some different domain, then transferring that knowledge and that model that's been built, and either taking the pre-trained model, doing some fine-tuning and applying it directly to this new application, or just taking the architecture and training it from scratch, maybe doing a little bit of hyperparameter tuning, small tweaking to the model. But in all cases, these are minor modifications that can be made to an existing deployable solution with the criteria or the one requirement that this new domain that you're mapping into, the problem is quite similar. And so while this set of work, it's tremendously important and it's providing huge gains in a number of different domains and industries which are able to immediately benefit from a deployable solution, what it doesn't address is domains like the SOC design space and the PPA prediction problem, where the problem attributes are so fundamentally different, you can't map some existing pre-trained model or existing architecture and directly deploy it on this new problem space. And so despite the tremendous amount of research, none of these are really getting at the heart of what the SOC domain requires. And this is what we're doing at Qualcomm. Rather than focusing on any one of these other three buckets, we're focusing on the intersection of breakthrough ML core R&D innovation and productizability. And the reason for this is what we found. This is what the PPA prediction problem solution really requires. It requires something which is fundamentally new and innovative in terms of the machine learning techniques in order to address the technical problems and challenges of the PPA prediction problem. But in order to truly fill out and meet our criteria of power, performance, area, and effort, that multiple objective, what we have to do is we have to do this research in a way which ultimately is efficient and can be deployed. And this is what constitutes our work today and will constitute our work going forward in terms of applying machine learning for the PPA prediction problem at Qualcomm. Thank you very much for your time and attention, and thank you for this opportunity to speak at the conference. I very much look forward to your questions.
Thank you very much, Lindsay, for a wonderful presentation. Yeah, just in the prior talk, we were discussing about the challenges involved in preparing the test data, right, for the machine learning or the training data. So I think you shed a good amount of light on that specific aspect that we were talking. So yes, I do understand a lot of invention has to go through to arrive at that kind of needed data. So I do have one question before that actually. Choosing graph neural network and represent the circuit as a graph is a breakthrough idea. I must admit to that. Do you see challenges in representing larger and or complex circuit as graph, and how do you plan to overcome those challenges?
Yeah, so that's actually, you've hit one of the key challenges. And that's why you see a lot of the research being done across the board where the graphs are being used effectively. It's on these smaller circuits. One, because that's the data that's available, but two, because it keeps the problem tractable. So it's definitely one of the biggest open questions that has to be addressed. And it's an open area of research from looking at, there's a number of different points of efficiency that we can look at with respect to training schemes, data preparation, sampling. So it's an open question, but it's one that definitely has to be solved to make these solutions deployable. And again, it hits at that green box on the last slide of why we can't just build enormous graph neural networks, because that's not going to be a tractable solution you can actually put in a real design flow.
Yeah, I completely agree to that. So yeah, thank you once again for staying late for the conference and giving your valuable time. So thank you so much, Lindsay.
Yeah, thank you for having me.
Thank you. Okay, So now moving on to the next talk. Um, so it's from Sandeep Deshpande. Sandeep Deshpande with 2 decades of experience in product development. He is a director at Silicon Labs, managing IoT platform software engineering. He is instrumental in leading companies' growth in design development of IoT products. So in his free time, he plays sports and practice yoga, and is also a acro yoga coach holding jam sessions across the globe. So his talk is based on edge intelligence in wireless IoT. So Sandeep, all yours.
Hello, all. I'm Sandeep Deshpande, Director of Software Engineering, Silicon Labs, Hyderabad, and I welcome you all to VLSI Design 2022 Embedded Systems International Conference. The topic we are going to discuss today is Edge Intelligence in IoT MCUs. We may often have heard of edge intelligence happening more on the clouds, more on the heavy beastly machinery, but here is where we would also be looking at uh, edge computing or the edge intelligence in IoT MCUs. Let's begin. IoT and digital twins. So this is a phrase which you may have come across in the past couple of years, especially with the advent of COVID. We all have seen a transformational shift in terms of the way we work, the way we approach to our business as well as personal lives. Work from home 2 years ago uh, wasn't that much of a norm as it has become now. The advent of IoT products, the advent of MCUs, the advent of edge machinery all over has been a revelation. Operational technology, as you can see on the screen, this is where most of us would be the consumers of the IoT space. If you look at the third balloon from at the middle, if you look at the car automation, is something that's a big thing which many of us would be using it on a day-to-day basis. We do relay important information from these devices over to the gateway. What would be a carrier? Could be a cellular, could be a wide area network, could be any other thing. But then huge amounts of data gets relayed on through the gateways, through the networks to data centers. Then they then pass it on to the analytics and probably to clouds or directly to public clouds. And then decisions are made, taken, and then the consumers are informed back. Billions of devices sending out data every few seconds. That's something to think about. Each and every bit of the data needs to be stored, however, temporarily or for a longer period of time, analyzed, and the decision taken. The further exponential growth of IoT devices in the past couple of years has actually led to exponential growth of data, all in all. Let's take a look at the post-COVID 2019 IoT world and how has it impacted each one of us. The number of IoT devices projected to be about 75 billion by 2025. There is a huge jump of about 5x times when compared with the pre-COVID era. Similarly, the cellular IoT devices have seen a jump of about 3x over the pre-COVID projections. The bar graph here suggests how these numbers have risen drastically. Uh, as you can see, there's a CAGR rise from about 13 to 42% in the past couple of years and the next couple of years to come. Artificial intelligence, edge, machine learning, deep learning, all these are the phrases very closely interconnected, as we all know. Artificial intelligence, a quick summary, is a technique which enables machines to mimic human behavior. For instance, we look at a particular object, observe it, and then start processing it, and then start making sense of the raw data, start taking some decisions. Artificial intelligence is tuned towards mimicking this aspect of human behavior. Then a subset of it is machine learning, the subset of AI techniques. They are based on statistical methods to enable these machines to improve with training and inference and all in all an overall experience. Deep learning is a subset of the machine learning which makes the computation of the multi-layer neural networks feasible, and this has led to a huge transformational shift in terms of how we are going to live the rest of our lives. In the past couple of years, as we all know, due to COVID, the consumer roaming quotient has come down a bit. However, the IoT roaming quotient has gone up considerably. What do I mean by IoT roaming quotient? The adaptation of IoT devices in our workspace, in our home offices, in our day-to-day norms, day-to-day errands we run, has grown exponentially. Acceleration in digitization strategies is something that is also coming at the forefront. Massive increase in work from home, supply chain pressures, huge demand on healthcare systems is also one of the major driving forces. These digitization strategies are here to stay, and the future risk is simply too great to avoid saying, you know what, we may not visit a similar world all over again. With that thought, let's look at how does an AI or artificial intelligence model work. There's something called training and there's something called inference. As you can look at it, there is a training model that is being developed on the left side of the screen, wherein a training data set in form of a cat's image is fed to the training model, and the model acquires this data set and tries to make sense of it, tries to divide it into smaller individual units and see how do we identify this particular data set as a cat or a dog or something else. Accordingly, the decision is conveyed, and the training model is a continuously adaptive process which learns over a period of time and then transitions into something called a trained model. This trained model then fits itself into the inference side on the right side of your screen. If you look at it, this is where, when the next time around a cat's image, the same cat or a different cat altogether, is sent across to this trained model, it does recognize it as a cat. And accordingly, there are applications and services featuring capabilities which you make use of these decisions and accordingly inform the consumers or the users of the IoT space. So today's heterogeneous networks are unable to manage massive growth's anticipated number of endpoints and data volume. So that's something that has that keeps pushing us towards something called edge computing. We'll talk more on it a little later. Let's first look at how can we keep on improving and improvising the training versus inference cycle. If you look at another set, there's a large n set of human faces that are brought forward. Accordingly, the model is trained. At times, it incorrectly recognizes it as a non-human category, and then the error is conveyed back, and that's how the label of human face is checked, and the training model grows in terms of predictability, in terms of reliability. AI end to end, what does that mean to us? There are challenges that have been created by pressing need to move analytical models closer to the source of data. Why is it so? Because we generate huge amounts of data in the IoT space, and each and every bit of data needs to be transported to the cloud or to huge MIPS intensive machines over there. At times you can call it the top edge or the middle edge, and then the data is processed, decisions made and conveyed accordingly back to the consumers. So with this huge impending costs, overheads, I think there is a growing and pressing need of moving the entire analytical model closer to the source of data. At present, IoT devices are not only proliferating but simultaneously increasing in sophistication. The increased demands of AI processes demand future IoT environments composed more than simple sensors with 8-bit microprocessors. If you look at the left end, this is the typical cloud infrastructure for an artificial intelligence, full set of data, wherein the decision analysis is also done at the cloud. Who are the typical consumers of this the cloud infrastructure? Are the retail store owners, for instance, the industry players, large hospitality chains, and whatnot. Then comes the top edge, where the regional set of data and decision making happens. This is typically a level, let's say, lower in terms of complexity and magnitude to the cloud, probably cities, municipalities, to monitor resources like water management, electricity, parking space, security, and whatnot. Then comes the middle edge, as we call it, and the middle edge is the on-prem of IoT networking application processors. For example, the Cortex A class for folks who worked on it or looked at it. Decisions made in household or buildings instead of sending it on cloud. For example, smart lighting. People who are working in huge uh, buildings or offices, when they walk out, the smart lighting senses that there are no more active human movement over there, and it slowly starts switching off the lighting system to save power. So that's a classic example of middle edge. Then comes the very edge, or the pure edge as we call it. This is the simplest end device, like small low power sensors, light bulbs, thermostats. Using Cortex M class, for example, a very, very teeny tiny AI ML system to make the best decision on data being sensed. So this is the model which most of the world is now leaning on. Let's see how that unfolds. What's the what is it at the very edge? Why the very edge, right? So ever increasing demand for small integrated solutions, high volume, cost sensitive markets. There's something called the empowered edge, as we call it, the AI-rich IoT edge devices all fall under this category. There is a growing need for small form factor. There is a growing need for battery powered devices, coin powered devices, and increased security. The moment you stop transporting data onto the cloud, there is a growing acknowledgement of an increased security at the premise or on the premise. Is edge gonna catch up with cloud? That's a debate for another day, but definitely edge computing is something that's growing and growing by huge margins. The if the latest statistical predictions and analysis are right or anything to go by, we are looking at about 40% of growth in the next 3 years. That's 2025. We would be looking at 40% of the existing IoT products on the edge. That's a revelation. There's an excessive amount of unstructured data which has led to this particular growth. What is all the more important is the standardization of things at the edge. How do we do that? So, for example, let's start looking at benchmarking things at the edge. What do people need as a typical use case, right? Human activity recognition, food classification, alphanumeric character recognition, keyword spotting, uh, emerging hardware needs, and a whole lot of other things. So, looking at this, how would a typical edge hardware look like? Purely based on benchmarking, purely based on the algorithms that run the AI ML infrastructure, the frameworks, there is a high level benchmarking done that Cortex M class would be a good specification. There would also be a need of, if not a heavy loaded GPU, probably a AI/ML accelerator, a MVP coprocessor in that sense, could be very handy in trying to start doing AI/ML at the edge. Typical RAM flash requirements, we'll talk about it later on, but with the existing IoT products, RAM flash requirements for the above mentioned benchmarking use cases should be suffice. There are ML frameworks, for example, TensorFlow, PyTorch, Keras, SparkML, and a lot many more, which are in play, and these would be part of the on-prem hosted environment. Moving on, how does it actually work? What are the numbers? So I'd like to exemplify one of the latest offerings of Silicon Labs, the EFR32 BG24 or the MG24 series. We launched this very recently with the objective of having target applications in the sense of having it fully loaded with AI/ML in terms of prediction analysis, in terms of the categories. I would say smart home is a major category we are looking at, build automation, lighting, portable medical devices, and a lot many more. It's a 20-bit ADC, it comes along with that, and as I said, MVP coprocessor. A little more deep dive, how does this work? Uh, as I said, this is an exemplification of EFR32 BG24, but any other AI edge device would follow the same line. So there are sensors who are continuously sensing, accumulating data, crunching numbers, and sending it to the processing unit. There are microphones in place, analog or digital camera and whatnot. And then the AI ML accelerator in-house built in the BG24 would look at training and inference in a sequential manner, and then the event detection ultimately happens. It's a pretty low powered solution. It saves a lot of bandwidth. There is no latency of to and fro over the network. Security is top notch with there is no with especially the need of not getting onto the cloud, as well as high end Silicon Labs security modules hosted. The cost also comes down hugely, and the inferencing goes up by about 2 to 4 times over a Cortex M, and the power of inferencing comes down by about 6 times. So these are great and encouraging numbers, and I'm sure there will be a lot more to come by. A particular AI/ML matrix vector processor, if you look at it, will not go into the details, but if you look at the AI/ML matrix vector processor here, the third one from the left at the top, this is where most of the offloading of the CPU happens. This is where I would expect the training and inference models to run and quickly a decision conveyed to the CPU. Let's look at a benchmarking of a couple of use cases again. Human activity recognition, as we mentioned about, let's say in the home security systems or anywhere else. The complexity would be about 70K MACC, which is about the multiply and accumulate complexity. It's a unit that indicates complexity of a DL or a model for processing. Food classification, if you look at it, it's about 90K MACC, and the memory footprint for the human activity recognition is about 6 KB each, RAM and flash at max. Again, these are experimental numbers, but these numbers across the industry are very encouraging. The food classification memory footprint for RAM is about a KB and flash is about 300 KB. That's also a very, I would say, optimal in every sense. Moving on. So Silicon Labs BG24 examples and partners, if you look at it, as I mentioned, there are a whole lot of frameworks involved. For example, TensorFlow. Then there are the AI/ML partners in SensiML and Edge Impulse who work along with these products. And they help us with signal processing, voice commands, low resolution, audio pattern matching, and whatnot. It's a very exciting time with COVID hopefully going down this year in 2022, and we all looking forward to meeting one another in person, conducting business with one another in person, And then with the advent of IoT, it's going to be a very, very exciting future ahead. I thank you all for patiently listening through this short session, and I'd be more than happy to take any questions coming by. Thank you.
Okay, great. Thank you so much, Sandeep, for such a wonderful talk. And yes, IoT is everywhere and has changed human life to a large extent. Uh, a- it is definitely a useful application for every human being, but more than that, it is also fascinating, right? So you see everything working autonomously. So when there are, I mean, with IoT, when there are several connected devices over the internet or on premises, what kind of security challenges you see, and how is it managed at Silicon Labs?
Great question, Rupa. First of all, let me thank you and everyone else involved in organizing such a great VLSI 2022 conference. It's been an honor to be here. Thank you, one and all. Coming back to the security aspect of IoT, yes, that's been a mainstay for quite long, and a lot of companies across the globe who are major players here have their own way of addressing it. If I were to exemplify Silicon Labs, we do have something called our own secure vault, as we call it, which is Silicon Labs proprietary stuff, and we try to offer solutions spread across PSA level, PSA group to level 2, 3 support. We've seen a very encouraging response from the field out there in terms of adopting IoT, whether you're looking at a mesh network, on-prem or cloud. And as security is always an ever-evolving subject, we would also keep an eye on that and make sure we are there when things arrive.
Okay. Yeah, understand. So for the audience, if you have any questions for Sandeep, you can use the Q&A box and send us the questions. Sandeep is here to answer any of your questions. Okay, so yeah, so I think um, we had a very good session as from you, Sandeep. Thank you so much, and yes, definitely we look forward for more and more innovations from you and and Silicon Labs. It's a wonderful talk. Thank you so much, Sandeep.
Thank you, Rupa. Thank you.
Okay, thank you. Just before moving to the next talk, we have one question from for Lindsay, our prior speaker. So can we have the question, please? Okay. So the question is, okay, are you using machine learning guided HLS? It's from Suhas.
Yes, it has. Hi. Yeah. So, we're looking at machine learning solutions across the full RTL through GDS verification testing framework. So it's definitely, we're looking across the board. And if you are specifically interested, there actually is a number of machine learning and heuristic-based applications that have published on HLS specifically. So it's an active area of research, not just at Qualcomm, but across industry and, a number of different companies. So it's definitely a important and interesting space where machine learning is being applied.
Okay. Thank you so much, Lindsay, for taking up the question, and thanks
Sure.
again for staying late. So
Sure.
yeah, thank you. Okay, so let's move on to the next talk. The next speaker is Mr. Umesh Nair. He's a director of design engineering at AMD, leading the CPU design team in India. He has nearly 24 years of experience in various aspects of implementation of microprocessors and complex ASICs. He has received 3 patents for innovations in implementation. Umesh will cover critical AMD technologies or products for high performance leadership. Umesh, over to you.
Thank you.
Recording stopped.
Right. Let me just share my slides. Just give me a minute.
Yeah.
All right. So good morning, folks. And thanks for that introduction, Rupa. So AMD's in leadership high performance computing. This is the cautionary statement. And I hope this session is not recorded, please. So if it is being recorded, do try to stop that. So AMD's mission is really high computing, and high performance computing is really transforming lives of people around the world. And the mission is, of course, to build great products that accelerate next generation computing experiences. So I'm going to go a little fast over some of the slides, and then we'll focus on some, and of course, can have questions at the end. For those of you who have not heard, I mean, AMD is 13,000 employees. So this is slightly outdated. Right now, we are actually just double that with the Xilinx stuff. So around 25,000 plus now. And the strength in India is also doubled with this acquisition. And yeah, high performance computing and it's really
sorry to interrupt you. Are you presenting something? We cannot see your PPT.
Oh, sorry. I thought I was sharing. 1 second.
And Umesh, I think the presentation recording has been stopped. So yeah, we have already instructed that. Yeah, now we can see your slides coming.
Okay. Thank you. Yeah, so I mean, I had some earlier slides, but that's fine. So yeah, I mean, we have moved to 25,000 employees, and with the Xilinx acquisition, and that employee strength is also doubled in India. This is a really interesting slide, and how AMD has progressed and got various awards over the last 4 to 5 years. Pretty much every award that's been out there, whether it's companies that are changing the world, most admired, and the last one, of course, most innovative company. And the tagline is where the best minds do the best work. So this is really nice to be in a place that achieves that. All right, I'll get, again, these numbers are may be changing, as we all know, but definitely data centers and PCs, huge addressable market. And this number is just going up by the year, right? So, all right, this is the area that I'll try to focus on in terms of technologies. The main 2 areas is really high performance compute, right? And CPUs, and of course, also we have a very strong product line on high performance graphics. So there are 2 lines. EPYC is moved to Ryzen, both of these CPU and CPU product lines, and in graphics we have Radeon and Instinct. So this is our Zen 3 core architecture. We do have the Zen line started with Zen, and then Zen 2, Zen 3, and Zen 4. Also, you can see on public. And this was really a 19% tech neutral IPC increase generation over generation. And there's a lot of reviews, and really driving high performance across servers, laptops, and desktops, right? A lot of advanced security features continue to be adopted, really, which is very, very critical across different markets. And really a lot of HPC and cloud, right? I guess AMD instances are now there pretty much across the board in any cloud providers' data centers. And this has been the roadmap. So, you know, Zen 3, as you can see, was in similar technology, and that number that I quoted was a tech neutral generational, which is phenomenal, really, like close to 20%. And of course, we are moving to 5 nanometer and beyond. So this is the compute architecture roadmap for the high performance. On the graphics side as well, there has been tremendous improvement, 2x performance compared to previous. And again, the new products also, you can find a little bit of public information, but yeah, and significant power improvement in the graphics space. And this was, again, all the numbers are generational, that RDNA to RDNA2. All right. And in terms of high performance products, pretty much every market segment, every industry, and you have these various items, right? HPC, which is high performance, enterprise IT, cloud, and so forth. And you see both AMD and of course the Ryzen is also present in these. So to talk a little bit about what really enables the high performance computing from our third generation AMD EPYC, which is Zen 3, it's really been the highest performance server processor, 2x better performance, with a lot of security. A lot of you would also have seen the Ryzen 6000 series, which was launched at CES January this year, which was the fastest Ryzen, hitting speeds of over 5 gig, and really the highest performance laptop with a whole bunch of security features as well, which really shows AMD's leadership in high performance. And this is the CPU roadmap. I think there's a little bit of product information there, Genoa 5 nanometer, but yeah, and so I think this is also looking very, very impressive, and it will sustain the high performance leadership in AMD. From a client focus, the main areas really is desktops, of course, with different gaming, commercial, consumer, and high-end, and notebooks, a significant market. And of course, the workstations in the commercial and consumer space. Really, this is enabled by the best processors. Again, this, as I mentioned earlier, 6000 is also launched at CES this year. But here we have all the 5000 in different areas, Threadripper in the desktop, and the Ryzen in PCs, which is the mobile processor refers to, and of course, even in Chromebooks. So really the full line of products across the board. This is a similar slide, so we'll just skip through that. Yeah, so this is AMD's path and motivation to have multi-generational product leadership, which we've kind of done for the last few years, and really high-performing notebooks, and have the end user experience to be very, very good. No security issues, etc. Right? Graphics. Again, this is a similar slide with different areas: PCs, Apple consoles, cloud, and mobile. All right. Yeah, I think this one I'm just going to skip through and come to the gaming roadmap. So there is this Navi 1x, 2x, and 3x products, which are the GPU roadmap. And this is the similar slide on the graphics side, where we are scaling and moving from the PC to the cloud, and our leadership stack, I mean the product stack, is really across different, from the value segment to the top performance. Okay, and then so yeah, and again this is, we do build the best innovative CPU and GPU solution, and it's been a multi-year story, generational improvement and leadership in high performance. The customer base and market share, I think all of you know about it. It's really grown significantly over the last few years, and so did the stock, thankfully. And it has been really consistent execution across all areas. And probably one of the fastest growing companies in the last few years, and expected to be in the next few as well. I'll spend a little bit of time on this slide just to talk about the India presence of AMD and the CPU design team. It's really, we do have a design team covering all the areas on the left and more. So right from RTL design, design verification, performance modeling, physical design, circuit design, design for test, and of course a lot of layout as well. And this team really builds a lot of CPU variants and focuses on CPU design, covers all the cache design, including the circuits. Also does some of AMD's multi-chip solution SoCs, the core complex, and really very key to AMD's product map. Very deep expertise across all domains. From we have engineers from NCGs to fellows in India, and fellows at AMD is very deep expertise, really very senior people. And the team is pretty strong, probably 300 plus now across all domains, and built over the years. The team also handles multiple designs in parallel for the CPUs, and a lot of focus and a lot of innovation papers and patents from the team in India has helped AMD a lot as well. Also, we do collaborate very closely with the team, though a lot of our programs are independent, but yeah, definitely there's a lot of cross-site collaboration as well. So I wanted to touch about the India presence because of this conference in India. And yeah, I believe this was my last slide. I know I went a little quick over the slides, but if anybody wants to go or ask any questions, I can definitely cover more in detail on any of the roadmap slides. Yeah, there is some links here that people can read a lot more about AMD.
Okay. Thank you so much, Umesh, for a great session and having us walk through various innovative products AMD is building and launching year on year. It's really great to see these kind of great products in the area of CPU and GPU, innovative products. So yeah, so from the audience, if you have any questions, please feel free to ask on Q&A tab. Okay, so one question though from my side, Umesh, is in terms of for SoCs, what kind of roadmap you see, if especially in the area of SoC building, because now with the kind of developments we see in the area of building or integrating multiple chiplets within the same system. So what kind of work AMD is doing in that specific area?
Yeah, great question. So I think there are multiple areas, multiple things that are happening. AMD has been a leader in the multi-chiplet solution. So that is one place where, it gives a lot of flexibility. And the reason for driving that is really, the technology and the cost as well, right? Do you want to put all your key IPs on an expensive process node, or do you just want to keep some of your where you really get the big bang for the buck? So that is one. So that is one way to look at, and you can split up your SOCs, and so our cores go in a different node and rest of. The second part of it is there are so many interesting packaging solutions coming up, right? So now we have the latest, which is called our Vcache, where you have a 3D. You can pack a bunch of cache, and if you look at the performance numbers, it's like amazing for high-end desktop and gaming, where you have an entirely huge cache which is stacked 3D. So I think this chiplet and packaging technology is really moving to the next level, and it's interesting, and companies can use that. So from an SoC design perspective, I believe there will be a lot of different complexities now, including die-to-die verification, die-to-die latency, package related issues, right? So it's becoming a different paradigm, and a lot of expertise, and we are finding things as we speak. So a lot of interesting things happening in that area.
Yeah, I myself work in the area of failure analysis. So we do see a lot of challenges people going through, and at the same time, innovating new ways of doing the failure analysis, especially in the SoC designs. So great talking to you, Umesh, and a wonderful presentation. Thank you so much.
Yeah, bye.
Thank you. Okay, so moving on to the last presentation of this session. So the next talk is from Mr. Subodip Bandyopadhyay. Subodip is General Manager responsible for emerging digital technology at UST. Subodip has 20 plus years of retail industry experience. He's a qualified chartered accountant and has held many different roles as CFO, CIO, and Chief Supply Chain Officer, e-commerce director within retail industry. So he will share a glimpse of how UST impacts the retail industry with a plethora of solutions under the umbrella of frictionless commerce and vision intelligence. So without taking much time, Subodip, over to you.
Good morning, good afternoon. My name is Shubho. I have my colleague Disha Kanchan joining from UST Emerging Technology team. We are going to talk about how UST helps transformation of some of the largest global customers in retail, hospitality, transportation, entertainment, and smart spaces. Of course, all using silicon and semiconductor technology. We are very happy to be today present in VLSID conference and happy to kick off the session for all of you. Today I'm going to introduce UST and what we do within semiconductor portfolio and take the discussion forward from there. UST was born digital. We started our journey in 1999, headquartered in Orange County, California. 30,000 associates, 140 global marquee customers. We are present in 29 countries and 79 offices worldwide. This is what we do within our semiconductor portfolio. You will see that we provide 360-degree silicon capability within pre-silicon, post-silicon, embedded software, lab management, tech support, IP and solutions. This is our core capability. And that's how we are able to support 8 of the top 10 companies in semiconductor business across 25 different countries today. Among the platforms, the one which we are going to talk about today is frictionless commerce and vision intelligence. And my colleagues are going to talk about what we do within 5G IoT space. Now, since my background is from retail and I worked in retail industry for many years, and within UST, my focus is building solutions focused on retail, QSR, hospitality industry. And today, retail is almost a $6 trillion industry globally. Who doesn't love to shop? All of us would love to shop, right? So from that perspective, our focus in today's discussion is going to be predominantly retail, hospitality, QSR. Of course, we're going to touch smart factories, industries, and all of that. But before that, a quick word about how the world has changed post-COVID-19. I mean, all of us know that what really has happened and what's happening even now. So we don't have to dwell on that, but we see that business leaders acutely acknowledge the fact that post-pandemic, online behaviors have changed, online offline behaviors have changed. The way customers expect retailers to behave today has changed. The shop floor employees, their job description has changed significantly. And as such, there's a tremendous shift the way customers and operators behave and operate post-pandemic.
Shubho, you spoke about the impact of COVID and some customer behavior becoming permanent. Where do you think a retailer should focus?
Perfect. This is a billion-dollar question. So, Disha, I would answer it in this way that the new normal for retail, QSR, hospitality, CPG industry, there's a significant shift between the consumer spending and the industry reaction. The digital dollars are all shifting towards building digital capabilities. Now we see that 2022 and beyond, there is going to be two significant levers which the retailers are going to play on. One would be a revenue lever, the other is the cost lever. Now, all of these things, the retail, QSR, hospitality, CPG industry, they're going to spend this digital dollar in clearly two different areas. One is building efficiency. How can you improve and augment efficiency of asset, labor forces, inventory, different processes? And the second one is customer experience. Inside store, online, a hybrid approach of click and collect, all of these things. So this is how I see that new normal for retail, QSR, hospitality and CPG is coming. So we have been constantly investing in building this capability on silicon. We call it magic of silicon delivered for business. And we are part of the emerging technology team. So we have built a slew of solutions, a slew of platforms, which can quickly scale up. So the first platform, Disha, is Vision Intelligence. The second one is Frictionless Commerce Platform. And the third one is 5G IoT solutions. So within Vision Intelligence, I'm going to explain that what we have built. And all of these solutions is essentially our significant allegiance towards a concept which we call AI on Edge. How can you use edge devices inside a store and deliver artificial intelligence in terms of computer vision, machine learning, deep learning models, and improve that performance and customer experience? So let me give you some example. So Vision Box, these are some of the examples. Because of confidentiality, I'm not able to share the name with you. But of course, these are some of the things which we have done. Now, if you peel the onion, as we call it, you will see that every single retail organization has got multiple security cameras, video cameras, infrastructure deployed to track certain customer behavior inside a store as well as associate behavior. We are working with them to build an infrastructure essentially dependent on edge devices with IP cameras and IP camera processes, where we take the same feed which is coming from their camera technology deployed already inside the store, process that data using our models which we have developed, and deliver significant business value. So we have built close to 100 plus different AI models today, which deliver all of these things, whether it is a retail organization or a smart factory. So taking the example of a smart factory, today we are able to do defect detection. We have done defect detection for millions of tires coming out of the production line for one of the largest tire manufacturer in Asia. We have done predictive maintenance for a large automotive company based out of Germany. Similarly, we are doing this smart inventory management for a retail organization today in Asia Pacific using Vision Box as a technology. So the core technology is all about computer vision and deploying that computer vision based technology at strength at a minimum possible cost, so that the solution becomes a solution which the retailer, which has got thousands of stores, they're able to scale up and take advantage of computer vision today. This is what we have built for last so many months. This is our capability for completely unmanned autonomous store. And I'm going to explain that through a video. We have built capability for vision checkout where we have deployed computer vision technology for solutions in a convenience store or an office cafeteria. But before that, let me ask something. So who wants to stand in a queue during busy lunch hour in office cafeteria for a plate of rice and something else, right? No one. So we understood that these are the touch points, these are the human touch points which need significant technology infusion, and have built a robust solution based on computer vision as well as gesture and voice technology, which can alleviate these pain points for customers. And these customers are, end of the day, customers like you and I who are standing in a queue in a cafeteria or in a convenience store. Now, obviously, we have to keep in mind that these solutions need to be well designed, so that they provide quick ROI for the operator and able to scale up. And exactly in the same way, we have built multiple other solutions within the genre of frictionless commerce. This is what research analysts are talking about, that we see that checkoutless stores, which will scale up, is going to be a big global opportunity for the operators to modify their business model. And modifying the business model essentially means reducing their operating cost and shifting those free cash flow to build digital capability. So this is where we see significant growth and traction coming towards these checkoutless stores. And let's see what we have built so far. So the first example which I'm going to play is what we have built, a fully autonomous store for a large retailer based out of Germany, which is part of the Schwarz Group. The second example which I'm going to play is the vision checkout example, what we have built. And all of these, both the things we have built in 2021. And these technology, both the technology, unmanned store as well as vision checkout, we deployed in a very recently opened store in Georgia, Atlanta. It's a public store where the store is called Nourish and Bloom Market. It's minority owned. And it's the first global hybrid convenience store approach. But let me play that video so that all of you can see what we have really built there.
Hello, I'm James Margrave with UST, and I'm here in Heilbronn, Germany, opening our newest autonomous store. UST has brought together the best artificial intelligence with multiple components to bring to life the most state-of-the-art retail experience for brick and mortar retail. With this experience, there's 3 simple steps. Scan in, shop as you normally would, and walk out. The journey begins by downloading the UST built interface. Shop.box customer app. Once your bank or card preference has been approved, you're ready to scan into the store using a QR code or tapping the card itself. Inside the store, shopping can take place as usual. Select items, return them to the shelf, or place them in your shopping bag. Upon exiting the store, your virtual basket is automatically calculated and a receipt is displayed on the UST customer app. Congratulations to UST, and we look forward to building our next store with you.
We're at the Curtis Hotel, a DoubleTree by Hilton hotel located in the heart of downtown Denver, where UST has successfully completed a pilot for the Vision Checkout device.
This device is absolutely perfect for the hospitality industry right now because you don't need to touch anything. You can simply use your finger to point and navigate without touching anything except for the snacks that you're going to be consuming. So going through a pandemic, this will certainly help with the sanitization of the products that we're using.
The success of this pilot opens up the way for a fully autonomous, touchless checkout experience at mini markets.
One of the benefits we bring with this technology is for mini markets, you build the database of vision checkout and then you can deploy multiple locations simultaneously.
UST has teamed up with a variety of partners to provide the most reliable self-checkout experience using AI technology.
Kiosk is in partnership with UST to innovate self-service technology solutions to solve pervasive business challenges spanning retail and hospitality.
Our ambition is to further roll out vision checkout services to boost sales and offer accurate data analytics.
We use Intel VPUs in our algorithms to provide the performance and provide the experience the customer is looking for.
Find out more about our products and services.
Vision Checkout is definitely a snapshot of the future of retail checkout.
Hi, my name is Jalea Hemmings, and I am one of the co-founders of Nourish and Bloom Market. We've been really excited to partner with UST that's provided our entire integration and project management services. UST has built our retail back office software, our full bistro module, and our kitchen operations software. In our store, we've deployed UST Vision Checkout, self-checkout, which is powered by vision, voice, and gesture. UST's product box has truly helped us with quick onboarding of our products and SKUs. UST's Cold Truth for temperature monitoring has helped us gain operational efficiency. We strongly believe in the hybrid autonomous store technology and believe this will allow us to scale faster and be better in the long run.
Well, thank you for that, Subodip. If you have any questions for Subodip, please feel free to write it down on the chat box.
Okay, great. Thank you, Shubhadeep, for a wonderful presentation. And the videos are the icing on the cake. It really, really showed us how the entire solution works so seamlessly, and it's such a boon for the human life. So yeah, if any of the audience has any questions, you can paste it on the chat Q&A tab. In the meantime, Shubhadeep, I have one question. So we already saw multiple kind of stores where you have implemented your solution. So what next? I mean, what is the plans in terms of near future? What kind of areas you want to focus on?
It's a very important and relevant question you asked. Our focus is essentially bringing that ROI at scale. So today, the adoption rate for all of this technology is very minuscule. So we are constantly working on computer vision and multiple other technology, IoT, 5G solutions, so that these technology gets adopted at scale and able to provide this robust ROI to the operators globally. So that's our focus. We can continuously work on that direction.
Okay, great. Thank you. Yeah, I mean, wish you good luck, Shubhadeep, and I see this being a wonderful solution for given this kind of a pandemic situation that we are going through. Hopefully, it is on the verge of ending, but it has given to a lot of innovations, and your solution is definitely a promising one. Thank you so much, and yeah. Thank you so much for staying up late, and I know it's post midnight for you, so thank you so much.
Thank you. Thanks.